Hello everyone, my name is Sid,
And I'm Savan.
and today we'll be doing feedback control. So let me just write down, we'll start with a discrete time system just because it's simpler, but the same ideas extend to continuous time. So let me write down a basic discrete time system. So you have x of n plus 1 is equal to a times x of n plus b times u of n, where A is your matrix that sort of determines how your state evolves from your current state, and B is a matrix that determines how your input gets into the system.
Great.
So a good way of visualizing feedback control is with block diagrams.
Sure.
So I will do that right now.
Here, I can draw out the block diagram.
Cool.
So basically you just got this nice block. This is your main delay block. See inverse. So so before that, you're adding together your x of n and your u of n. So that goes in here. This guy is x of n plus 1. So you know that x of n plus 1 is equal to a times x of n. This is your x of n. And that guy goes back in here. And then finally you got your b. And that goes over here, and your u of n goes in there. Great.
Bingo. So a good way to, I've got a lot of questions related to block diagrams. A good place to start from is to do exactly what Savan did, to start with the z minus 1 block and just construct the z of n plus 1 is equal to, is a delay into z. Or in continuous time, it would be like x dot goes into an integrator, s inverse, which becomes x. That's a good place to start, and from there, you can use your various equations to continue from there on.
Great.
Cool. Erasing that.
All right. So we got this guy, right?
Yeah.
So we refer to this as our open loop model. Although we call it an open loop model, you see that there is a loop that is closed. It's a little bit confusing, but you can think of it's open loop because your u of n does not have any sort of like anything that causes it to change.
Now, given this open loop model, how would we want to better take advantage of the system? So the A is given to us, the B is given to us, but we don't really have control of the states per se. We just have this input, which is like this knob that we can tweak. So given only the input, can we make the system behave in a way that we want it to behave? Okay, so we have this open loop model, and we have this fixed matrix A, this fixed matrix B, and we'd like to control the system in some sense. And the reason we'd want to do that is, imagine we've just been given the system from out of the blue by someone, and it already has initial state and it's evolving in a certain way. The only knob I can tweak then is going to be the input u of n, and I would like to be able to, say for example, make the system evolve in a way that is stable from this point onwards. And a good way to do that would be to use my current state information to sort of like force the system like organically to be stable, for example.
Yeah.
So what's a good idea that, what's an idea you think we can do to do that?
Well, so there's only two things that we have here, right? We can't really see anything inside of this open loop, right? This is sort of a black box to us. So the only things we see are your x of n and your u of n. So a natural thing to do is, why don't we just connect them?
That's a pretty good idea. But wouldn't you want to have some flexibility in connecting them too?
Yeah. So let's connect them and throw in a matrix in the middle, right? That seems reasonable. So when we do feedback control, what we're doing is we're taking our state, we pass it in through matrix K, and we take that and then we feed it in here. And usually we like to keep our u of n as is. So you add it, you put in another u of n, or let's call this guy r of n, and we put it back into our open loop model. So although we drew in an r of n, a lot of times in this class we won't even, the r of n will be just 0. And we'll be talking about how we can, manipulate this K matrix to do what we want it to do.
Exactly. So RFN is this, if you still like to continue having a knob, say if this system was connected to an output matrix and you'd want to somehow control the output in a particular way, that's where RFN comes into play. But for this class, usually RFN is 0.
Yeah.
So if you were to use this new system model with this K matrix, this system would become x of n plus 1 is going to be equal to a x of n plus b times k x of n.
Right. So
plus
we're
r of
basically,
n.
that's just feeding that back.
Exactly. So this was the u of n from the previous input. It was this thing. And now we've replaced the u of n with k. This is x of n. This is k x of n. And we're passing it back and adding r of n into it. So expanding this out, this becomes a plus bk x of n plus b r of n.
Perfect.
Now, the advantage of putting it in this way is with this matrix K over here, we now have flexibility in controlling how the system itself evolves. So our state transition matrix is now something that we can control.
Perfect.
Cool.
So we've effectively just changed our state transition matrix entirely, right?
Exactly.
So question, Sid. What can we do with this? Like, why do we want to change the state transition matrix at all?
Well, typically it's because we're usually given a system that we really can't change in any way whatsoever. So we try, and that system is usually unstable. And the typical thing that we do is to try and make the system that we're given, that we have no control over, evolve in a way that's stable so that we can actually control it.
So take unstable system and make it stable.
Make unstable systems stable again. Sorry. No? Okay.
So you can take an unstable system and make it stable.
Mm-hmm.
What about making an uncontrollable system controllable? Can I do that?
That's a little tricky because you kind of like inherently rely on controllability to be able to place your eigenvalues wherever you want. So when you're passing in x of n into the K matrix and making that your new input, you kind of depend on the controllability of A and B to be able to get your state to wherever you want it to be, which is kind of like implicit within the controllability condition. So if you are controllable, you're definitely guaranteed to be able to find some K that will make your system stable. If you're not controllable, that does not mean that you cannot find a K that will make a system stable, but it just means you're not guaranteed that.
Okay. Cool.
You look a little upset at my answer.
I think that was a reasonable answer. It was very mathematically correct.
Okay. Well, typically we want A and B to be controllable. If it's controllable, we can definitely find a K that will allow us to place our eigenvalues wherever we want.
So feedback control works best if you have a controllable system, yeah?
Exactly.
Okay. That was what I was kind of trying to get at.
Okay.
Okay.
Okay, cool. Do you want to move to a question?
Yeah, let's move to a question.
All right, so let's do a question. So we have a pendulum, an inverted pendulum here, which let's say has an angle theta from the mean, theta from say the 0 position. We have a small ball of mass m. This is of length L. And because of how physics works, you have a force of mg sine theta going this way. We pretend we have this small nozzle. And I like seeing the word nozzle because Savin doesn't like it. Over here that can spew out fire and give you u of t in this direction. Give you a force u of t in this direction, which sort of like allows you to have tangential acceleration along this way. And we're going to try and construct a system model for this. For the sake of making this problem easy, we're going to pretend this thing doesn't have any noticeable length difference from this center of mass, and it's just basically magic in a nutshell. Let me just write an L here because I forgot to put that earlier. The state equations, the most important part that govern the system, is right over here. and Salvin will construct a system model for this.
Great. So we just did some magic physics and got this. We don't expect you guys to be able to do the physics, so we're not going to do the physics here. Great. So now that we have the physical equations, let's make a state model. As you notice, we have theta, theta dot, and theta double dot in this. So we're going to need at least two state space variables, namely theta and theta dot.
Cool.
So on the left-hand side, we have these guys, and we have d theta d dt of those is equal to, well, the derivative of theta is just theta dot. The derivative of theta dot is just, well, it's theta double dot over here. So this ends up being minus k over m theta dot plus g over L sine theta minus u of t over ml. Perfect.
Cool. So as you notice, there's no A and B matrix in this yet, and that's because this is not really a linear system because of this sine theta term.
True.
And so if we ask you to construct a system model and it's not obviously linear, we expect you to write something like this in this form.
Yeah.
Cool. Now, the next thing we're going to do is linearize the system.
Go ahead, Sid. It's all you.
Okay, I see what you did there. Just to make things easier for myself, I'm going to say theta is equal to x1, theta dot is equal to x2, and then I'm going to say f1 of x1, x2, and u is going to equal to theta dot, which is x2, and f2 of x1, x2, and u is going to equal to this thing over here. And that's equal to minus k over m theta dot, which is x2, plus g over L sine theta, which is sine x1, minus u of t times ml, which I'll just leave as u of t divided by ml. Cool? Everything good so far? So when we're constructing the matrix of the derivatives, we're going to use f1 and f2. So I'm going to make you calculate the derivatives, and then I'll put it all together. It shouldn't be that difficult. So we need to find df1 over dx1.
So let's write out what our Jacobian looks like first,
Okay.
right? So our Jacobian, our A matrix, will end up looking like df1, dx1, df1, dx2, df2, dx1, and df2, dx2.
Remember, we're evaluating the derivatives at the points that we want to linearize about, which
And
I
then-
guess we didn't really talk about.
Right. So we should note that we're linearizing these points about like theta equal to 0 and theta dot equal to 0.
Because in the ideal situation that we want to get, we kind of want this pendulum right over here to sort of like stay in this position, which is theta is equal to 0, and not really deviate about the point, which means theta dot is equal to 0.
Right. Okay, so we got this. All right, so evaluating these partial derivatives, df1, dx1 is 0. There's no dependence on that. This guy is just 1. df1, dx2 is just 1. df2, dx1, so that would end up being this
G
guy.
over L evaluated. G over L cosine of x1 evaluated at 0, which is just...
I'm just going to write it in first.
Okay.
And then df2, dx2 is minus
K over M.
And evaluating this at x1 equal to 0 and x2 equal to 0, you end up with 0, 1, g over L minus k over m.
Awesome.
And then last thing we got to do is find our U matrix. Sorry, our B matrix.
Okay, let me just write it down here so I can clear out some space. You have 0, 1, g over L minus k over m as our A matrix.
Perfect.
Cool. Then erasing the bottom here. How was your day last night, Salvin? It was St. Patty's Day, wasn't it?
It was.
What do you do? Is that why you're so tired today? Ha. It's easy to give Salvin a hard time. It's one of my favorite things to do. Okay, let's try and find the B matrix. So we have the B matrix is going to be df1. I guess on D it would be the funky D. df1 over du and df2 over du. This one's going to equal to 0. This one is going to equal minus 1 over ml, which implies that B is going to be 0 minus 1 over ml times u of t.
Well, just our B matrix is this guy.
Oh, yeah, just
Yeah.
a B matrix. Sorry, that was my bad.
Yeah. So B equals 0 minus 1 over ml.
To be and not to be. Okay. Cool. I can.
Let's just move on to the next slide.
Okay. Okay. New slide introduced. Salvin, what exactly? Now that we've linearized the system, what exactly are our state variables?
Well, we linearize at an equilibrium of 0, so we're looking at small deviations from the 0.
Yeah. So in other words, we have theta is equal to our theta, linearized theta, which is like the small deviations about this point, is theta minus theta star. In this case, it's 0. And theta dot linearized is equal to theta dot minus theta star dot. What? Okay. Which is also equal to 0. So in this case, it doesn't really matter. We can still use theta and theta dot. It just because we're linearizing about the 0 point, it's just really convenient to continue using theta and theta dot. Cool?
Perfect.
Awesome. So 7, is the system controllable?
Let's find out. So what does our controllability matrix look like? Well, so we know our C is, you have your B and then you have your A, B, and it's two-dimensional, so those are the only ones we had.
Mm-hmm.
So our B is 0 minus 1 over ml, and then A times B is
Minus 1
minus
over
1 over ml. This guy is
minus k times m times minus 1 over ml.
that one.
There's a minus 2 there. Because minus 1 over ml?
Oh, sorry, yeah.
So
So
just
this is
think-
just positive.
Yeah.
Cool. Yeah, so we got this guy.
Uh-huh.
So is this full rank?
Yes. Because
Yes. Because, if we did the row reduction, it would work out. But you can also see it simply because, you can subtract it and finagle the numbers such that it works out.
to put it in non-hungover thousand terms, because of the 0 right over here, it's pretty straightforward to conclude that these are linearly independent, these two vectors, so they must be full rank. And just to mention this to make sure that, just to remind you, the reason why we have to only go B and AB and not any further is because of a theorem called Cayley-Hamilton, which says that A squared B, A cubed B, and so on can be written as some linear combination of B and AB. So if you're working in n dimensions, you only have to go B, AB, dot, 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 A, n minus 1B.
Yep.
Cool? Awesome. You can do this. I believe in you. Okay. He hates me right now. So now we've shown that it's controllable. So we can try and linearize not linearize, we can try and design a state feedback model. Okay. I actually like that. I don't know why. It reminds me of Dragon, if I were to just add scales somehow.
Okay, all right.
Never mind, I'm going too far. So now we can design a state feedback model. And from our derivation, it's basically, we're looking at something like A plus BK. We're going to assume we just want to stabilize it around the center point, so our R of n is 0.
Yes, so what you mean is that our system looks like
Yeah.
this, right?
Mm-hmm.
Okay.
And just to be pedantic, we have B R of t, but since we don't want to really do anything with it, we're just setting this to 0.
Okay.
Cool. Awesome. Let's. What are the dimensions of our K matrix?
Well, our we need the dimensions of our A to match the dimensions of our BK matrix, right?
Okay.
And so if our B is 2 by 1,
Mm-hmm.
then our K has to be 1 by 2.
Cool. So let's say K is K1 and K2. Awesome. Okay, let me just erase some stuff. So we have a model d by dt x is equal to a plus b k1 k2 times x of t.
Perfect.
And I can erase this too. Okay. Now for simplicity, let's just put in values to our G, L, and K. Let's say.
Let's not. Let's keep it symbolic.
Okay, you're doing the calculation.
All right.
Okay.
All right. So our A plus BK.
I don't know why he did this, but I'm really happy he did. I'm just gonna laugh at him the whole time. I'm not gonna help him one bit.
So our A plus BK matrix, you have 0, 1, G over L minus K over M.
Mm-hmm.
Plus, so your B, this guy, times K, you end up with 0, 0, K1 over ML, sorry, minus K1 over ML, and minus K2 over ML. Great. So putting this together, you just end up with A plus BK is equal to 0, 1, G over L minus K1 over ML minus K over M. Geez. Minus K over M minus K2 over ML.
Nice. Now it's up to you to find the determinant of this matrix to place the eigenvalues.
Oh, yes.
And you have to do it symbolically because that's what you promised the people.
I did. So finding, we want to put the state feedback such that the eigenvalues are stable, right? Before they were unstable, we want to make them stable now.
Okay.
Don't we, Sid?
I gave you an easy way out. I don't know. Okay, let's do this.
Okay, so
let's watch you do it.
All right, so we're looking at the determinant of A plus BK minus lambda I, and we're setting that equal to 0. So it's the determinant of, let's see, minus lambda 1, G over L minus K1 over ML. Minus K over M, minus K2 over ML, minus lambda. So you end up with lambda squared. Yes. Lambda squared plus K over M plus K2 over ML, all of that times lambda, and then plus K1 over ML minus G over L. So I set the K1 and K2 values such that these, you can stop laughing now, Sid.
So we want the eigenvalues to be at -2, which means that we want our characteristic polynomial to look like this. Lambda plus 2 is equal to 0. And expanding this is lambda plus 4, I think, is equal to 0. Yeah? So now, because from 16a, you know that polynomials kind of form like a linear space, and these coefficients are linearly independent. We can just directly
map them.
Exactly.
So you have 4 equals K1 over ML minus G over L. So your K1 is equal to...
I'll just put an M and M here just to make things simple.
Sorry? Okay.
So it's 4 ML plus 4ml plus gm. Yeah.
Perfect.
And then your K2 is going to be...
So for this guy, you have K over M plus K2 over ML
Just to make things simpler. Oh, whoops, my bad.
equals 4.
Okay. And like last time, putting an L and L, we get
So you end up with
4ml minus KL.
perfect.
Cool. We actually did it symbolically. I'm impressed.
And it wasn't so hard, was it?
It would have been easy if you had numbers in. You have to admit that too. But yeah, so now we have, if we had an ideal rocket like this, we would be able to actually control our system. Cool.
So feedback control is great. We were able to take an unstable system and make it stable. So you can make a pendulum balance. And
with an ideal rocket. Sorry, it's just funny. I like seeing that. I'm sorry if antagonizing Salvin. I'm officially apologizing on camera. It's just really funny. Usually what happens instead, like if you do 128, instead of having a rocket like this platform itself moves. And I think the final design project is to do this very
the final lab is to solve this problem and make a pendulum stand up.
Yeah, which is pretty cool, right? Awesome.
Cool.
Thank you for watching. Good luck on your midterm.